This video goes through the process for deriving the geodesic deviation equation using a two-parameter family of curves on a general manifold before generalising the result to space-time. The resulting equation is shown to be dependent upon the Riemann curvature tensor. It then looks at the weak field slow speed case of the geodesic equation and how it relates to the Newtonian geodesic deviation case. So a geodesic generalises our familiar idea of a straight line in Euclidean geometry to curved spaces. So in flat Euclidean space, a geodesic is a straight line whose tangent vector points in the same direction as it is parallel transported along its length. In curved spaces, a geodesic is a curve whose tangent vectors remain parallel to each other as they are parallel transported along the curve in infinitesimally small incremental steps from lambda to lambda plus d lambda. So on the sphere, geodesics take the form of great circles, two of which are partly shown here in red. Notice them converging, and then as they pass through the North Pole and continue on, they will diverge again, unlike the parallel lines of Euclidean space, which remain the same distance apart forever. Alright, now in general relativity, all objects not subject to non-gravitational forces travel along geodesics. That is, all freely falling objects move along geodesics. They respond to the curvature of space-time. And that's what we mean by gravitation. The equivalence principle tells us that in a freely falling, non-rotating laboratory that is occupying a small region of space-time, the laws of physics are those of special relativity. So put another way, the local effects of motion in curved space-time are indistinguishable from those of an accelerated observer in flat space-time. So an observer in their laboratory, she can't tell the difference between a gravitational field, the acceleration due to a gravitational field, or if their laboratory is being accelerated in a flat space-time where there's no gravitational field. They can't tell the difference between the acceleration produced in either case. So the question is, how can an observer determine whether or not they are in curved space-time? Is it altogether impossible, or is there a way of working it out? Alright, now in curved space-time, the paths followed by freely falling objects are geodesics, or paths that are not the straight parallel lines of Euclidean geometry. And that means that we can expect these lines to converge or diverge when observed over a large enough region of the space-time involved. So let's say we have our laboratory with an observer in it, and two test masses are released in the laboratory and allowed to rest. The whole laboratory is freely falling towards this mass here. Now, if the observer observes for long enough, over time, she will detect that these masses are moving closer together as the laboratory moves through space-time. Now this effect is called geodesic deviation and is produced by the tidal gravitational forces that draw the objects of freely falling objects towards each other, draw the trajectories, I should say, of freely falling objects towards each other or away from each other. Now what we want to do in this video is quantify this deviation. Right, so let's start with a congruence of geodesic curves on our manifold, and by congruence we mean that for any point P on the manifold there is only one geodesic passing through it. So the entire manifold is covered by these geodesics, and at any point on that manifold there is only one geodesic passing through it, but altogether they cover that space. Now geodesic curves are solutions to the geodesic equation, which we have here, and here geodesics will label them capital G and parameterized in terms of the parameter lambda. And the direction of increasing lambda is this way for us, for this video. Alright, now let's form another curve crossing the geodesics, and this curve will be parameterized in terms of the lengths s of the curve. So we'll use some parameter that reflects the length of the curve. So in space-time, such a parameter would be the proper time of the particle travelling through the space-time, but here we'll just call it s, and the direction of increasing s is from left to right. So we have a curve passing over these geodesics. Now let's form a congruence of these curves so that we have a family of two parameter curves, x mu lambda s, and these are our curves, mu being equal to the dimension. In 4 dimensions we'll have mu is 0, 1, 2, 3. Alright, and they will form a congruence. So there's one, so at any point P on the manifold here, there's only one of these curves passing through it. Alright, tangent vectors to the geodesic given by this object here, dx mu d lambda. Remember that the geodesics were parameterized in terms of lambda and times the basis vector e subscript mu. Now, and so diagram here, at the point P, here's a tangent vector here to the geodesic. This tangent vector lives in the tangent space to the point P, so it exists in the tangent space to the point P. And the tangent vectors to geodesics are parallel transported, so they satisfy the condition that the covariant derivative of the tangent vector is 0. And what that means is that the tangent vector is parallel transported along these geodesics, and that means that the magnitude and the direction is held constant as the vector is moved by infinitesimally small steps of d lambda as it moves along the curve there. And that's what it means to be parallel transported. At each point along the curve there, the tangent vector will live in the tangent space to that one point. Alright, now the tangent vector to a geodesic satisfies the condition of the covariant derivative of the tangent is 0 and parallel transported so that the tangent vector in the direction, the scalar product of t dot del t is 0, meaning that the object is parallel transported in the direction of the tangent vector, hence t dot t. So the projection in the direction of t dot del t gives us 0, and that leads to, if we expand that out now in terms of the basis vectors and components, put in, so the tangent vector is t mu e subscript mu, dotted with the covariant derivative operator, differential operator, e nu d dx nu, and then the tangent vector t gamma e gamma. Alright, if you notice here, this scalar product here, the Kronecker delta applies, so that's Kronecker delta nu mu, and so we contract over that, and that gives us down here t mu d dx mu t gamma e gamma, and down here we'll replace the partial derivative with the covariant derivative to generalize it to all points on the manifold. And so we have here, this object is a vector. Now at all points on the manifold, the basis vector will be non-zero because there will be a basis vector at each and every point. And so for this to be 0, for the object to be parallel transported in the direction of the tangent vector, hence this dot product, scalar product of the tangent vector with the covariant derivative of the tangent vector, for that to be 0 means that the components must be 0. So this expression in here must be 0. And that's how we get the condition that geodesics satisfy. Covariant derivative of the tangent vector in the direction of the tangent vector is 0. Alright, now the tangent vector of the curve C at P is V is dx nu ds e nu. At the point P here, here's the vector V. This vector points towards the geodesic next to it, but to get the actual displacement vector, then we need to form the product. The actual displacement vector from P to here, to this point, to the next geodesic, is V ds, the increment ds, the infinitesimal differential ds here, the little distance, is a displacement vector between neighbouring geodesics. Now, just a word of caution here, on a manifold, basis vectors vary from point to point. It's not possible to do addition and subtraction of vectors. Okay, so but we'll talk about that very shortly. We can talk about an approximation. For an infinitesimally small separation, we can talk about a reasonably valid approximation, but the actual operations of vector addition and subtraction are not defined on a manifold. They simply don't make sense, unlike in flat space. But nonetheless, this quantity here, V multiplied by ds, the differential, the incremental differential, infinitesimally small differential ds, will gives us the displacement vector from the point P to the neighbouring geodesic, approximately. Alright, so let's look at the changes that occur between the 2 points P and Q on a single geodesic. If we notice here, here's a tangent vector in red, and we notice from Q to P there, the tangent vector is parallel transported, so it satisfies the condition that the covariant derivative of t is 0. So this magnitude and direction is held constant as it's moved by infinitesimally small steps along this geodesic here. Slowly along we go, little bit by little bit, holding the magnitude and direction constant, and that's parallel transport, so that's that condition there. However, del v, covariant derivative of v, and the increment ds, the infinitesimally small increment ds, the differential ds, is not 0. As this is carried along with the tangent vector here, it will vary. It's not constant at all, and this product here in general will be non-zero. The basis vectors are going to vary from point to point along here, and so this differential here will not be 0. Alright, in flat space though, the tangent straight lines, parallel straight lines, a straight line parallel transports its own tangent vector. It's a constant, so dt, d lambda, the partial derivative of the tangent vector with respect to the parameter lambda will be 0. And v here, this is this product v ds, that's the vector displacement from one geodesic to the other. This distance in here is constant for parallel lines in flat Euclidean space, and so the partial derivative of this product here, dv ds, will be 0. There's no change in this vector as it's drawn along the geodesic here, pointing towards a neighbouring geodesic, because these parallel lines in Euclidean space are the same distance apart and pointing in the same direction all the way along, and so this vector v, the derivative of that will be 0, but not in curved space. Alright, so the change in the vector v in curved space is due to the intrinsic curvature of the manifold that it is tangent to, as it is transported in the direction of the tangent vector, and that just means that the vector v, the basis vectors will change from point to point. So the covariant derivative, which has contains both the partial derivatives of the components, but also the partial derivative of the basis vectors, that will not be constant from point to point. That will change. Now, given that geodesics are infinitesimally close to each other, it means that the rate of change in v can be approximately seen as the relative velocity of the two geodesics, and shortly I'll develop an argument for that. Now, this is because a derivative involves the difference between two infinitesimally separated values of v in the limit as that difference goes to 0. So I'll just remind you the derivative of a vector here, in general, is dv ds, as the limit as delta s approaches 0 of this object minus this over delta s. So you can see that this is the value of v in one geodesic minus the value in its neighbouring one. Alright, so an image of that here is the vector v at this point here. Here's the vector v in the neighbouring geodesic here, s plus delta s. Alright, and delta v is dv ds is the limit delta s of this over this. Okay, that's the total derivative, because so in curved space we will have to consider the variation in the basis vectors as well as the variation in the components. Alright, now here's our separation vector between neighbouring geodesics. So here's our test particles in our laboratory freely falling in a curved space-time. And notice that the separation between them decreases as it approaches this mass here. Now the vector v lies in the tangent space to the point in question, but by forming the product v ds we form a vector that points from one geodesic to its neighbour. A displacement vector from one geodesic to another, but with the caveat that the operation of subtracting vectors in a curved space-time doesn't make sense. So as an approximation though, the point v at s plus ds is very close to the point at s. So when you have neighbouring points that are infinitesimally separated on a curved manifold local to the point P and to little points ds around it, the space appears roughly flat. And so as an approximation, we say v ds is dv ds ds is the limit as ds approaches 0 of this object here. These ds's cancel out and we're left with, and I say it's only approximate, but so long as the ds is small, infinitesimally small, then this minus this is approximately valid, because the space, imagine on a manifold, the point P and a second point Q very, very close to it, infinitesimally close to it, then you could roughly do the vector subtraction. It's not absolutely true, but approximately true. Note that for any 2 points P and Q, the Christoffel symbols are not equal at the different points. Okay, but so long as P and Q are very close to each other, it's approximately the case. So this product, delta V times ds, is approximately this minus this, which you can see as the, if you like, the relative velocity of the two geodesics. Alright, so relative velocity of geodesics, delta, t dot del V. This is the relative velocity as we evaluate delta V as it's moved in the direction of the tangent vector. Okay, putting in the components for this object here and the basis vector. Now the relative acceleration of geodesics, A is t dot del V, delta t dot, the covariant derivative of delta, and writing that out again is this, the basis vector. Now, at every point on the manifold, these two tangent vectors form a suitable system of coordinate basis vectors, because remember, at each point the tangent vector and the vector v lie in the tangent space to that point, and so they can form a suitable coordinate basis vectors, not orthonormal, but coordinate basis. So that means they're not necessarily of unit length, and so they have a commutator equal to 0. Alright, now let's evaluate the components of that commutator. That's this object here, and generalising it to a manifold, we use the covariant derivative here is 0, and that implies that this arrangement here is equal to this one. Now the component part of the relative acceleration of our geodesics vector is, so here's the relative acceleration of our geodesics, and that becomes this object here, and that's this, and where gamma, delta with contravariant gamma, put this object in here, which came from here. Alright, next object then is, we notice that this was equal to this, so we can remove that and place that in there. And now what we're going to do is, this first covariant derivative will act on this product in here, so it will act on the vector v, and then it will act on times, so the product rule or Leibniz rule is applying here, so this acts on this times this, plus this and the vector v times the tangent vector component here, and then this covariant derivative acts on this part here, times t mu v nu. So we get this object here. So there's the product rule or Leibniz rule in operation there, operating on this product here. Alright, now the Riemann tensor, separate video for all this and so on, but it is defined there in other videos on this channel, but by definition the Riemann tensor is defined this way, and what we can do is rearrange that object, and so we'll take the first part here, move this second term here to the right, and we have this object here. So let's continue our argument. So the relative acceleration of the geodesics is this object plus this object, and what we're now going to do is, where we had one of these before over here, we're now going to replace this one with this term on the right, these two terms on the right, put that in there, and then again, write this out again, plus this business here, times that, plus the Riemann tensor times this part here. Now we can generate a new expression for the middle term above, that's this one here, we're going to generate a new expression for that, and we're going to have that this object here, if we carry out the Leibniz rule or product rule again on this object, we will have this times that, plus this object here, which is just this part here. Alright, and then what we'll do is we'll subtract this first term on the right here from the term on the left here, and leaving us just this bit on the right here, which is equal to this object minus this object here. Alright, so just keep that in mind. We'll move on to the next page. Alright, so returning to our relative acceleration again, this is the component of that vector, is this object here. There's all of that, substituting back in. Now, we need to do some things here. So we have first term here stays, and then over here we have this part here, which is this bit here. The reason this term dropped out is, if you look at it, this is the geodesic, this is a condition that geodesics satisfy, and we know that this is equal to 0. So that bit's dropped out. That's gone to 0, so it's disappeared. because that's the condition that geodesic satisfied, because that's equal to 0. So that bit drops out, and we're left with this term here, and we're left with this term here, and the Riemann tensor part times the components of the tangent vector and the vector v. We've got that object now. Now, let's factorise out this common term here. Put that out here like that. And we're left plus Riemann tensor part over here. Now we notice we recognise this as the commutator, the components of the commutator. So we write that in here, times the factor we pulled out earlier, plus the Riemann part here gives us this. And that gives us the Riemann tensor times this object, because if you remember earlier, the commutator was 0. So this part went to 0 as well. And so the relative acceleration vector component, A gamma, is equal to the Riemann components, Riemann tensor components, and this object times these factors here. Next bit, so our final result is the geodesic deviation equation, so the components of which are a contravariant gamma is this object here, the second derivative of the vector v is equal to this object here. Alright, now, for a particle with mass, this equation can be expressed using the proper time parameter tau. That's the time measured by the particle that carries a clock with it and measures its own time, where the manifold is now space-time. So the tangent vector is now the forward velocity u alpha of the mass. So we replace the t here, the tangent in this case becomes the forward velocity of the particle as it moves, freely falling particle in curved space-time. There's its forward velocity, that becomes tangent to its world line. That's this object here. Alright, now, so here's the geodesic equation of space-time manifold. Now, let's have a look in the weak field and slow speed limit. This result should correspond with the Newtonian deviation equation. So let's take the weak field limit. So proper time becomes coordinate time, gamma approaches 1, and the forward velocity in that case, which is defined as this, becomes c, gamma approaches 1 here, so it becomes 1 there. And the spatial components, because it's slow speed, this is approximately 0. It's much less than the speed of c, so that it's relative to c, this is roughly approximately 0, c0, and just u superscript 0, contravariant 0, the time component of the forward velocity, this part here, u0, is equal to c. And so let's go back to this equation here and substitute in what we now know. So the alpha and the mu, alpha and mu will be 0 because it's u0, the rest is 0 from the 4 vector. Put that in there, and u0 as we see is c, so u0 times u0 is c squared, put that out front, and we have this object here. So here's the relative acceleration vector component, but in the slow speed weak field limit. We get this object here, and we're hoping that's going to agree with the Newtonian version. So the Newtonian geodesic equation here is our laboratory here. Now the paths followed by the test masses are x of t, coordinate time t, and the second particle over here is x of t plus v of t, the separation vector. Right, the equations of motion for these masses are the acceleration is phi the potential energy, the Newtonian potential, phi as a function of position, dxj, and here the indices are made to balance, so the j and the j sum out, leaving us with I, matching this one over here. So it's a valid equation, so the Kronecker delta ij is just put in there for the indices to match. For the second particle over here, its equation of motion is this. Alright. And next line over, we can approximate the gravitational potential, Newtonian gravitational potential, phi x plus v by a Taylor series. So phi at x plus v is 5x plus d phi x dxk vk plus higher order terms. So the difference of the two equations from before gives us this part for the second particle on the right minus the first particle here. That's the acceleration there. The difference in acceleration between the two is dvi dt squared. That's the separation vector. The acceleration in the separation vector, how that changes in the Newtonian case, will be this object minus this object. Two negatives here. We should rearrange this a little bit. Plus, put that out front, minus this part here. Okay, and now we're going to replace this d phi dxj of this object here with what we found above. So we're going to have delta ij ddxj of this object here, the Taylor series we found from above, put that in there. And when we do that, what we'll find is that this first term we'll cancel this first term and we'll be left with this object here. Ignoring the higher order terms, just the first order, we have this object here. So the second partial derivative of the Newtonian potential times the vector k, the indices here, Kronecker delta applying here, so that matches with what we have over there. Alright, next bit. Now, resulting in the acceleration vector is this object here. Gives us this is the Newtonian case, and the relativistic low-speed weak field geodesic deviation equation is, in the low-speed case we found this earlier, and so the Newtonian geodesic equation, just repeating from here above, we're going to compare these two now. We can see that this suggests that there's a correspondence between the Riemann tensor and the second derivative of the Newtonian gravitational potential. So there appears to be a correspondence between these two. I should just say here, this is what we found earlier, is this part here from up here. What we can do is that we can swap these two indices, that 0 there and that j, but then we, by the symmetry properties of the Riemann tensor, we must have a negative here, so put that negative in here, and that's handy because that will cancel with this one here. And then what we are left with is this object here is equal to this, 1 on c squared, factor out here. Now, we can just go a little bit further, but this showing us that very much throughout this whole process in our curved space-time, it's the Riemann tensor, which again reflects the curvature of the space and appears ultimately in the geodesic deviation. It's down to the inherent curvature, the intrinsic curvature of the space that causes the deviation in the geodesics, and that's why the Riemann tensor appears in what we found so far. Okay, so that's relating this to the Newtonian case. Then after contracting on I and j, we get R00 is this object here. This here, using the flat space metric, we contract because we're in Newtonian space, we're in flat space time. In the weak field limit, so where there's weak field, so there's little to no curvature is what we mean by that. The curvature is minimal to 0. And when we contract that, we get what looks like the Poisson equation multiplied by a factor 1 on c squared. But inherently running through the variation, the change in the geodesics as they move through the curved space-time is very much down to the Riemann tensor.